Welcome back from the break. Now it's time to dive in to the definitions of P0 to P4 subdivision of hybridization. Before we jump into that, we'll talk a little bit about the degree of hybridization and their features. Degree of hybridization is the ratio between the electric motor power and the engine power. An electric vehicle has a degree of hybridization of 100% because we have no engine at all in it. So motor power is giving everything to the wheels. The implemented hybrid concepts in cars have a degree of hybridization varying between 15 to 55%, and then we have true mild hybrid concepts that have a degree of hybridization in between 2 and 15%. The features of a conventional vehicle is that we don't have stop and go traffic where we can shut off the engine, but the micro hybrid we can do that. Then we have the mild hybrid where we do have regenerative braking and higher voltage, and then we have electric motor to assist the conventional engine, and finally in the full hybrid then we can drive the vehicle using only the electric machine. Finally, we have plug-in hybrid electric vehicles where we can use the wall plug and we have 32 kilometers of range on electricity. Coming to the classification, it relates to the electric machine position, whether we have it in P0 here, we have just a bigger generator, bigger electric machine that can support more frequent starting, more frequent charging than regular machines. Then P1 here, it sits on the engine, so it cannot be decoupled from the engine. At P2, we are able to run it on pure electric drive. We don't need to drag the engine in case we want to have all electric drive. Then PS here is power split, where we have a power split device. And P3, then the electric machine sits on the output shaft. And finally P4 is if we have all electric here, so we have all electric drive. And the electric machine of course drives the vehicle forward. We have this subdivision. Micro hybrids are parallel because we have only one mechanical flow. In the mild hybrid it's the same thing. And when we come to full electric in terms of the parallel hybrid, then we're running it like this. And then in the power split we have the two different machines. We have the generator and here we have the electric machine like the Toyota Prius. And when we come to the plug-in, we have a smaller combustion engine and a bigger battery and bigger electric machines in relation. And we can have a serial hybrid where we can decouple the engine and we can charge the battery, where we can decouple the engine and generate the electricity from only the motor and run the vehicle with only the electric machine. With the range extender, we are designing the vehicle for mostly electric drive, but we add a combustion engine to increase the range so that we can cover up the limited range of the battery electric vehicle, but we can have a quick refueling thanks to the power that's inside the chemical energy of the liquid fuel. In the PX classification we can have front wheel drive, so we have P2 in this case here, and we have rear wheel drive and the P3 where we have it on the output shaft, and we have electric all wheel drive or ERAD where we have the electric machine on the rear shaft, and we have all wheel drive where we have electric machines both on the rear and on the front, and the combustion engine is also going on the rear and on the front. This list is also included for your reference so that you can sit and look at it and you can do it together with the slide for the electric machine positioning. So I will not go through the material here more than, as I said, it's for your own reference that you can work with at home if you are interested in looking up more details about the things. The next thing we will go into is the battery and look at the state of charge, and also cover some constraints that you will need to handle in the hand-in assignments that you are about to solve. So the state of charge for us with cellular phones are pretty well aware what the state of charge is and that we need to charge it when it gets depleted, etc. The full range is 0 to 100%, but in many hybrid electric vehicles a much smaller range is used. To estimate the state of charge is a fairly difficult and much studied problem, state of health, that is used to say what is the health of the battery and how much energy can we get in it and how much power can we take out of the battery. When we look at plug-in hybrid electric vehicles, they are usually going with higher ranges than 50 to 70. They are going maybe from 10 up to 90%, but still they are saving the edges. I will come back to that in a couple of slides. When we look at charge depletion, charge sustaining and blending, these are three strategies for controlling the charge. The basic hybrid vehicle needs to be charge sustaining because we cannot charge it from the plug. So when we make comparisons for a hybrid electric vehicle, we must make sure that the state of charge is the same before the cycle as it was after the cycle. And this is very important for making fuel comparisons, so we're really comparing apples with apples. We should not cheat by starting with a full battery and then deplete it over the test cycle. Plug-in hybrids though, they are not charge sustaining and they often operate in two modes. One is charge depletion, and then when it has depleted the charge to the lower limit, then it goes over to a charge sustain region. So this is an illustration showing the World Harmonized Light Duty Test Cycle, WLTC, and here we have in solid, here we have charge sustain, so we're keeping the charge at the same level, so it starts at one level and it's the same level when it comes to the end. And when you have the other strategy, the charge depletion strategy, we start up here and we empty the battery as soon as we can, and then we go over to charge sustaining. And finally, you can run in what's called blended mode. Then you're aiming for getting to the end of where you're going with the state of charge emptied there, so that you can start charging when you have reached your destination. And many people have shown that the blended strategy is what gives you the best fuel economy, because then you can save some electricity to the points where you really need it the most during the cycle. And here you can see how the internal combustion engine is used. In the blended strategy, we have a lot of electric energy in the beginning, so when we have light loads, we're using it a little bit because it's inefficient to utilize the combustion engine for loads. And when we come up to the point in the cycle where we have more power requirements, that's when we jump in and can use the combustion engine to gain fuel economy. So this has the best fuel economy of them. And then when we have the charge depletion, then we're running all electric all over here, and then we have to run the combustion engine down here because the battery is empty. So this strategy from here to the end, they are more or less the same, as you can see in the sketch here. And then on the charge sustain strategy, we have such a low state of charge so that we need to run the combustion engine to do some recharging, and then we can run a little bit all electric on some instances here because we have such light loads in those occasions. We're talking very much about battery, and we will jump to the battery and the standard model as we have discussed previously. So the standard model that we'll utilize is that we will have an open circuit voltage here, which is an ideal source, where this open circuit voltage, you should know that this open circuit voltage depends on the state of charge. And then when we start to load it, either if we're taking out current or if we're charging, then we will get resistive losses in the resistance here, and we will get varying terminal voltage. So the terminal voltage is the state of charge dependent open circuit voltage minus the inner resistance times the current if we are pulling energy from the battery, or the other way around, plus if we are pushing energy into the battery. So having the right sign of the current here, you get that. In the course, we will work with the assumption for the hybrid vehicles you're looking at that we are operating in a narrow region around 50% as the normal hybrids are doing, and motivated by these cells, we say that there is not very much variation with the open circuit voltage in relation to the state of charge. So we neglect that impact motivated by these A123 batteries. But once again, you should know that there are variations, and there are cells that have quite a lot of variation in voltage with the state of charge. Then when you go up here and you start to charge up here, this is where you could destroy the battery. So avoiding charging up here is something that you should do, and also avoiding to discharge it too much over here, because that is also killing the battery. We'll look a little bit more into that in the coming slides. But the main thing is, if we are keeping the operation of the battery here in the central part, then we're saving the battery life because we're gentle to the battery. Motivated by this, we will have flat behavior. We say that this one is indeed constant in the exercises, and then we have to account for the resistive losses that we have in the battery. And this is the model that we'll use in the hand-in assignments in this course. But once again, I want you to be aware of this dependence. Coming to the currents, we see here the charging of a 28 ampere cell. This is the manufacturer safe charging when we are in the normal condition. When talking about batteries, we say that they are doing their best in the same conditions as us human beings. They like to be in the same temperature region as we are. About 20, they are pretty okay. When we're charging the cell, if it's close to empty, we can charge it with a high current up until we come to higher state of charge. Then we have to reduce it to not kill the battery. And then we have the temperature aspect. If it's too high, we're not allowed to do anything with the battery to avoid having an explosion. The same thing when we go down here in temperature, we see that it's colder and colder. Then we have to reduce the charging. So we cannot charge with a lot of current if it's cold. And especially at really low temperature, we are not allowed to charge anything at all. When we come to the discharging, it's a little bit the same, but this battery can take out 3C in discharging when we are up here. But when the temperature drops, we are not allowed to take out much more current, especially not when we are down at low state of charge. This is how you should treat the batteries. When we are in the normal conditions, then we can utilize the energy of the battery. And you see here that this one has a higher capacity for discharging and a lower capacity for charging. So we cannot charge at the same rate as we're taking out current in this case. So things that are controlling it is temperature, state of charge, and current are very important factors for keeping the battery alive. The C rate is the rate with which we charge a battery fully in 1 hour. So if we charge the battery with 28 amperes for 1 hour, then it's full. So 28 amperes is 1C for this particular battery. This one is allowed to charge a little bit above 1C, but there are batteries that we can charge with 2C. That means that we can charge the battery completely in half an hour. And 3C, then we can charge the battery completely in 20 minutes. And here we see how much we can take out of the battery. Smaller C rates and operation in a SOC window near 50% is good for the battery. And if we're just operating and utilizing a few percentage, we're carrying around a larger battery pack than what is needed to achieve the fuel economy benefits. But we achieve a longer life of the battery and of the vehicle. When we come to your hand-in task, we are not looking at temperature, but in the hand-in assignment you will need to keep the state of charge in the allowed state of charge window that is given in the exercise, and we need to keep the battery current within its limits, and we need to keep the electric machine within its limits. So here we have the electric machine diagram where we have maximum torque, so there's a maximum torque limit, and here we have a maximum power that we need to maintain us within. And then there's also in some cases a maximum rotational speed that we're not allowed to go over. For the combustion engine we have the same thing. We have a maximum torque, we have a maximum speed, and we also have a lower speed, because if we go down below 800 RPM, the engine will die because it goes below idling. So that's some of the things that we need to consider when we do the implementations of the hybrid electric control strategies. Then we come to the average operating point method that you have already encountered in the hand-in assignment, but I wanted to save a little bit for this when we have talked about hybrid and the opportunities with hybrids. So in the hybrid operation, and the average operating point method is that we look at the cycle and we come up with the power that the vehicle needs. When we know the power that the vehicle needs, we can go to the gearbox, we take the gearbox efficiency, then we have the auxiliary efficiencies, then we have the combustion engine efficiency, and then we come here. And what we're looking at here when we are loading the engine is that the cycle in average might end up in some point here. So we say that the cycle has this average requirement of torque and it has this average engine speed. Then we take the data for that point and we use it in the average operating point method to get the fuel economy estimate. When we use hybrid operation, like all electric drive and load shifting and a range extender, we would like to place the engine, so when we're running the engine, we would like to have it operating at its maximum point. And when we don't need the engine, then it's better to turn it off, because then we're not consuming any fuel at all. So that is a basic thinking behind like the range extender. So we do all electric drive, and then when we need the extra energy, we go up and run the combustion engine in the most efficient points. And we also have here the load shifting. We see that the fuel consumption decreases if we can shift the load up to higher points. So when we're running the vehicle in low loads, we run all electric, and then when we need to have higher energy, we go up, and then we do load shifting so that we run the vehicle on the combustion engine, but we recharge the battery a little bit, so we're lifting the points up in the map here. You will work with this hand-in assignment and you will do one average operating point analysis to see how it works against the more advanced cycle methods. So there's one hand-in assignment for the IC-based vehicle, and then when you design the control strategies for the hybrid electric cases, you can see and analyze load shifting if you're interested, and you can see how it's shifting around the system. If you look at the engine maps here, they look pretty non-linear. Then you might ask, they can't be good because they are so strange looking for just taking one point and then using that point as the estimate of the total driving. Well, the thing is that the Whillen's line approximation, this Whillen's line approximation, replaces the entirety of this map. So this is actually the same thing as this map. The thing with this linear behavior is that if we are operating on this line, so say that we are operating back and forth here, up and down, driving around, that means that while we're operating and we're doing averaging over it, the average point will lie on this line. So we will be on this line, and the average energy and average fuel will have been ended up on this line. So then this average point will be on the line, so then it's within the model. So that's why it works so well for the average operating point for conventional vehicles. But when we come to hybrids, we can, for example, operate with a vehicle in engine off, and then we jump up and we try to load at this point. This is the most efficient point that we have. And we switch between this point and then we turn the engine off. Then it means that we are operating on, like this line, if we can ideally switch between this point and this point. And if we in average would need this much energy, that would mean that we would be like operating on a virtual line here, because we're switching between this point and this point, and the place that we're getting will be, and the energy that we are generating will then be closer to the maximum efficiency of the engine, because that is where we are generating all the energy that we need, and then we're storing it on board with, of course, a penalty. So for hybrid electric vehicles we need to do something more advanced, but for conventional vehicles, the average operating point gives us numbers in the right ballpark due to these reasons. So with that, I have finished lecture number 3. So we can take it easy for some time, and then we will come to lecture number 4 that will contain deterministic dynamic programming, which is a benchmark method for optimizing powertrains. And that deterministic dynamic programming is the crown jewel of this course. So welcome back for that lecture. Bye bye.